a cyan filter absorbs the red light and so lets through the blue and the green. Similarly, if we use a magenta filter absorbs the green, letting through the blue and the red. So what we see as magenta is blue light and red light. There is also, we can put a yellow filter in, and this is important. We see that what we perceive as yellow light is, in fact, light that is missing its blue. The green and the red are present, the blue is absent, and we see yellow. And so if we superpose the yellow and the magenta filters, the yellow filter absorbs the blue, the magenta absorbs the green, and what is left is red. And indeed, superposing those two filters, we get red. If we superpose yellow and cyan, the yellow absorbs the blue, the cyan the red. What's left is the green, and we see that very nicely in this picture. And we can keep playing. We can superpose the cyan and the magenta. The cyan absorbs the red, the magenta absorbs the green. Putting them on top of each other, we're going to be left with blue. So this has to do with the way our eyes see colors. The important thing for us to take away here is that a filter that absorbs the blue looks yellow. We cannot distinguish this yellow from the yellow in the spectrum there in between the red and the green that is pure yellow light. We saw that, as Young showed us, light is a wave, and also as Young showed us, our eye, in fact, has 3 color detectors, one sensitive to red light, one sensitive to green light, and one sensitive to blue, and what we perceive as color is merely the relative intensity at which those 3 detectors are excited. So yellow light that excites the red and the green approximately equally, because in the spectrum, yellow light is between red and green, cannot be distinguished from a combination of actual red and green light. And so our eye, unlike our ear, is not a very good Fourier analyzer. So much for biology, but this will be important in understanding some phenomena later. And then, once we know that light is a wave, it's not too shocking that color is a property of the wave. Color turns out to be the frequency of light. Visible light has a frequency of order 10 to the 12th hertz. Even at the rather high speed of light, we can compute the wavelength is pretty short. It's between 400 and 700 nanometers. A nanometer is a billionth of a meter, 10 to the minus 9 meter, and these are the units in which typically we measure the wavelengths of visible light, at least in astronomy. And so 400 nanometers, the shortest wavelengths, visible light is the blue light, as this indicates, and the red end of the spectrum is the longer wavelengths, and the order of the colors in the rainbow is according to their wavelengths, so that violet light, in fact, is at the short end of the spectrum. Green is somewhere in the middle, around 550 nanometers is green light, and so on. Now, for something completely different. We talked about gravitation as the force that dominates astronomy, but in most of our lives, gravitation of the Earth is important, but when we interact with each other or with objects around us, gravitation is completely unimportant. The gravitational force of a human being is negligible compared to the other forces we interact with. The force that turns out to dominate most of physics is electromagnetism, and so we need to understand some things about this. And the simplest version of electromagnetism is the force between 2 static charged objects. So there is in the universe a thing called electric charge. Some objects carry electric charge. You can charge your hair by combing it on a dry day. And the annoying force that makes your hair stand on end on a dry day is this electrostatic or Coulomb force, which has a formula that will appear familiar. The force between 2 objects of charges Q1 and Q2 is given by a constant times the product of the charges divided by the square of their distance. This might appear familiar. It's that square of the distance again. It's not exactly a coincidence. The big difference between electric charge and mass, or between Coulomb's law and Newton's law, is that Newton's law, remember, had F equals G m over r squared, and these numbers were positive and the force was attractive, always. Gravitation is a universally attractive force. Coulomb interactions can be attractive or repulsive. It turns out that the force is attractive when the 2 charges are of opposite sign, so positive and negative charges attract. and charges of like sign repel with an equal magnitude, but the sign, the direction of the force, depends on whether the charges are equal or opposite. This in turn explains why this force does not dominate the universe and this force does. It's not because gravitation is stronger. In fact, we have an invariant measure of strength under which gravitation will be a far weaker force than electromagnetism. But because opposite charges attract, most objects are neutral. In the presence of charge, if you have something that's charged positively, it will attract negative charge until such time as it reaches equilibrium, in other words, is neutral. This is not possible for mass. There is no concept of negative mass. In fact, it's worse than that. We'll discuss the instability of gravity. This will have profound consequences, so I'm not just belaboring an obvious point. And charge, like mass, momentum, energy, etc., is conserved. You can neither create nor destroy charge, though, of course, charge can be transferred from one object to the other. So when you comb your hair, the comb is charged with one charge, your hair with the opposite charge. When atoms form an ionic bond, they exchange charges and so on. But the total charge in the universe, or in any enclosed region in the universe, is conserved. And then, you see, in gravitation, I kept wanting to talk not about the gravitational force, but the gravitational acceleration. So you talk about the Earth, for example, generating around it a gravitational field. The gravitational field is the statement that were a mass to be placed there, it would experience a force. And you can compute the force per unit mass without knowing what the size is of the mass that you would introduce. And in a similar way, you talk about an electric charge producing an electric field, which is the force per unit charge that would act were a charge to be placed there. So a charge creates an electric field around it, because another charge, were it to be brought there, would be affected, and a charge is affected by an electric field. A similar phenomenon of a field, a region around an object in which other objects might be impacted, is encountered with magnets. A magnet creates around it something that we can call a magnetic field. In the presence of such a field, any other magnet, like this little compass, will align itself in a particular direction at any given point in space. Of course, it will align itself so that its north pole faces the south pole and so on. And so we can imagine that this region of space has some property called a magnetic field, which is the statement that were you, remember there was a field here even before I brought the compass, that told you that were you to bring the compass, it would point in such and such a direction. Now, magnets and electricity initially appear completely unrelated, and it is known, however, that electric currents, in fact, produce magnetic fields. In the vicinity of an electric current flowing around a coil behaves very much like a magnet. We call this an electromagnet. And we see that we have a magnetic field in the vicinity of an electric current. Moving charges create magnetic fields. So this is the first relation between electricity and magnetism, but there is another relation, which is that if you have a changing magnetic field, it will cause charges to move so that this magnet has absolutely no impact on the charges in this coil. But if I move the magnet so that the magnetic field in the coil changes, then while the change is ongoing, current will flow, and current flows means there's a force on these charge carriers. This implies an electric field. A changing magnetic field causes an electric field, and I can, of course, cause the change by moving either the magnet or the coil. And so changing magnetic fields essentially can be thought of as generating electric fields. This has profound consequences. Let's see what they are. The fact that moving charges can create a magnetic field was discovered in 1820 by Ørsted, and it turns out that moving charges are also affected by magnetic fields. We saw that when we moved the coil in the presence of a magnetic field. Faraday realizes the phenomenon that we were discussing, which is that a changing magnetic field is tantamount to an electric field. 30 years later, Maxwell writes down what are the collected set of equations describing electric and magnetic fields, and in particular the phenomenon he needs to add is that a changing electric field creates a magnetic field. In the presence of a changing electric field, there's a magnetic field. And the combination of these two phenomena leads in Maxwell's equations as part of the solutions to propagating waves. Propagating waves in which essentially you set up a changing electric field which creates a magnetic field, which creates an electric field, which creates a magnetic field. You solve the differential equation that this leads to, and you find that it describes a propagating wave, and Maxwell computes from the properties of magnets and currents and Coulomb's law, properties that had been measured in the lab. He can compute the velocity of these waves that he's discovered, and their velocity, surprise, surprise, is precisely c. He didn't get it this precisely, but it coincides with the speed of light that Fizeau and Foucault had measured 11 years previously. So Maxwell has very good reasons to imagine that he's discovered that light is a wave, as Young said. In fact, we now know what it is a wave of. It's an electromagnetic wave. The disturbance that propagates in space when a light beam travels through it is an electromagnetic wave, is a disturbance in the electric and magnetic fields, which have come to take on sort of a life of their own. Remember, they were ways to calculate what would happen if you put a charge, and suddenly they create each other and they propagate through space far away from the charges that might have created them in the dim, distant past. They have essentially their own existence. And so we do talk about these fields as important objects. The understanding that light is an electromagnetic wave also tells you that you can, in principle, imagine oscillating a charge or creating an oscillating electric field at any wavelength or any frequency. So we know that we see light from between 400 and 700 nanometers in wavelength. What about the solutions to Maxwell's equation with wavelengths outside this region? And it turns out that there is an entire huge electromagnetic spectrum out there, ranging from, at very high frequency and very short wavelength, gamma rays with wavelengths of down to 10 to the 14, 10 to the 15 meters and below, except below that are very hard to produce, through the X-ray spectrum that runs from wavelengths